what it took for her to get a visa, but it had a happy ending because she's here with us, and she's going to talk about SPOReS. And actually, like, I'm a mathematician, and one of the many things I admire engineers for is their creativity in coming up with acronyms. So I'm curious what it will be.
All right. So can you guys hear me? Yeah. All right. Okay. So I'm an assistant professor at the Indian Institute of Technology, Bombay, and so what I'm going to talk about today is a project that the government of India has funded. It's called the scheme that's funding it is called the Mission Innovation Smart Grids Challenge Scheme, and they are really looking for the focus, the NSF equivalent of the Indian funding agency, which is the Department of Science and Technology. They have recently changed their focus, and they really want to fund research which would have some sort of technology transfer happening. So SPOReS is one of the projects they are funding, and there's a big focus on what would be the end impacts, so to speak. And so it's a very interesting project. It's just recently started, so I just wanted to use this project to talk on this platform, primarily because the SPOReS team comprises of a lot of mathematicians, people from the CS background as well as engineers. So I thought this would be a good platform to introduce the project. So I'll quickly do a bit of background and motivation for the project, introduce some key components of SPOReS, and talk about one particular problem that I'm working on as a part of SPOReS, and then present some concluding remarks. So quickly into the background and motivation. This is a very messy diagram of the Indian power grid. It's a fairly big system. We have over 1,700 generators, over 1,500 lines over 400 kV. If we were to model the network at 11 kV and above, then that would be roughly now I think 7,300 buses. So it's a very large network, and it's very complicated because a lot of our generation is government owned or owned by private entities. Transmission is primarily government owned, whereas we have a lot of private players as well as government players in the distribution sector. So it makes the system a bit, there are a lot of the same people who are setting the regulation also have sort of interest in running the business. So it makes it very interesting in terms of what sort of regulations come about and what really happens in terms of operating the system. In the global context, now some of these numbers may be old, so I know that the national grid was about 80 gigawatts about 10 years back. I couldn't really find very recent numbers on this, and I didn't do my homework very well, so I apologize for that. But it's a fairly big system, especially if you compare it to some of the big systems in the US like the PJM or the Midwest ISO. We have roughly 330 gigawatts of capacity now, generation capacity. Even then we still have issues in terms of supply shortages. A lot of our metropolitan cities, barring Bombay, still face. Is there a something? Huh. Let me see. So is it coming from here?
Because it's the blackout. It's an housing predicting.
Shall we continue? Is it too disturbing? All right. So, especially if you think of it in the context of the PJM or Midwest ISO systems, which are one of the bigger interconnection systems in the US, we have 330 gigawatts of installed generation capacity. Even then, we do have supply shortages. A lot of majority of the metropolitan cities in India still have roughly 2 hours of supply shortage, which is quite a bit of an issue. I don't know of many cities except the city I am in, which is Bombay, which has continued supply of electricity and a very high quality supply of electricity. Complicating this is the vision that our government has for where we should head next. We want to add about 175 gigawatts of renewables. Actually, this number is now going to be changed. It's going to be 225 gigawatts, but we don't know the split yet, so I'm still going by the old numbers. The currently what's published outside online is that we'll have 175 gigawatts of renewables by 2022. It's to be split between 100 gigawatts of solar, 60 gigawatts of wind, and 15 gigawatts of other things. Concurrent with that, we would need a lot of corridor for excavating that power, so they also have some green pathways, they call it, in terms of the transmission expansion for the network. And because we still have last mile connectivity issues, last few governments have focused aggressively on rural electrification. They've been trying to solve last mile connectivity issues, trying to first get the wire to the distribution transformer, then get from distribution transformer all the way to end users. And I hope some government would also work on ensuring that electrons actually flow on that wire, so that the consumers actually get electricity for a reasonable amount of time of the day. So right now there are still places, quite a few places in India, where the supply only exists for about 2 hours a day or 3 hours a day. So that's really, I don't think that's good connectivity, good grid connectivity. It's just a very poorly connected grid. So a lot of the Power for All program solutions really are decentralized energy solutions, where they have sort of worked out solar, wind, hybrid systems combined with batteries to sort of make power available to the consumers. But this is challenging by itself, because as soon as the grid comes in, their economics go for a toss and then they run out of business. So they have a lot of problems in terms of ensuring continued consumer base for the decentralized energy solutions. Very recently, the government also announced a policy of electrification of all vehicular transport. So that means cars, buses, and that's the mandate for that is 2030. So which means the grid is going to be exposed to a whole other bunch of new resources which come from these from having all vehicles electrified. Concurrently, we have also had programs in terms on energy efficiency. So there's a big Ujala program where we distributed a lot of light and LED based lighting appliances and other sort of efficiency appliances, and as I said, rural electrification as well. So this all of this, how does this really translate into what SPOReS is doing? So first, let me just introduce what SPOReS is. It's smart planning and operations of grids with renewables and storage. We have skipped a few of the important things just to come up with the acronym SPOReS. It's essentially a project that's primarily funded by the Department of Science and Technology, but there's a big chunk of funding available to do international collaboration. So we can actually host researchers from some countries, not all, but some countries who are a part of what is known as the Mission Innovation scheme. There are roughly 23 countries in here, US, UK, and a few European countries are already a part of Mission Innovation. So all the partners we have here belong to countries that are already belonging to the Mission Innovation scheme, and we have 2 industry partners here as well. So this is a big team. The team is led by myself and Professor Kriti Ramamridam from IIT Bombay. Kriti Ramamridam comes from a long history of working in CS. Over the last 10 years, he's been working on a lot of problems related to smart energy management. So we basically have this project going on now with 5 key components. There is a planning aspect to the project, where we want to come up with a planning tool which can help guide capacity additions, help figure out whether policies make sense or not, really effectively evaluate the impacts of policies. Professor Ankur Kulkarni, who is also visiting the Mathematics of Energy Systems program with me, he is one of the key collaborators on this project with me. And we want to be able to capture key interactions between stakeholders in the electricity business, so to be able to deliver this planning tool. The next component we have is this brown box. This is essentially a means to convert a blackout to a brownout. So whenever we have a supply shortage, the usual way to handle the supply shortage in India is to just roll the blackouts. You supply to feeder 1, then the rest of the feeders sort of get no supply, then you move the supply to feeder 2, and that's how you do it. But instead, if we were able to do load prioritization at all levels, right down from consumers all the way to the feeder level, then essentially we could provide reduced supply at all levels, and instead of having just supply available at each feeder for a small amount of time, you could have reduced supply available at all feeders for all amount of time. So that's one part. Then we also have a storage manager being developed, which would essentially figure out how storage could be used to complement renewables, how it could be used to complement other supply side resources as well as demand side resources. So this is essentially storage management algorithms. We have a lot of hardware being developed to emulate inertia, and not just emulate inertia but try to do it as inertia on demand concept, so that we can better provide support to the grid in the event of disturbances. And then to coordinate a lot of these operational solutions, we also have a signaling framework which would then dictate in normal as well as contingency events, how do all of these resources actually work. Whether if you had a supply shortage, do you discharge the battery or do you just do load prioritization, what actually effectively works. So we have something that would help figure that out in real time as well. A lot of these, so just to put things in context, the project has just started less than a year ago, so a lot of these things are still in developmental stages. I will talk about some of the things that are at a fairly advanced stage of development, primarily the planning tool. So how does this align with the national targets that I just talked about? If you look at the Indian grid today, we have increasing demand that comes from all the programs that we are running in terms of power for all, rural electrification, possible electrification of the transport sector. We still have supply shortage, which leads to these rolling blackouts, and we don't really have storage on the grid, and there is poor coordination between how our state grids are controlled and how the national grid is controlled. So what we want to do with SPOReS is come up with a set of methodologies, hardware solutions, software products that can really help the government meet the targets that they've set for themselves in terms of high penetration of renewables, ensuring demand for all consumers, and transport electrification. So a little more on the motivation and see how SPOReS connects to it. Just recently in I think April of 2018, the Delhi government introduced a new regulation. They now want to penalize power distribution companies for unplanned outages, and the penalty is supposed to increase as the number of hours the outage exists. So for the first hour, they are supposed to pay 50 rupees per hour per consumer. For the next hour, it would be 100 rupees per hour per consumer, and so on and so forth. That's how it's supposed to go. This regulation has already been proposed. Now the only debate is when would it actually come into effect. So this is very interesting from the distribution company's perspective, because the distribution company also has other problems to deal with. We have something called as the deviation settlement mechanism in India, which means that we do a day ahead schedule. We have 15-minute intervals over which the utilities and the generators schedule themselves one day ahead of real time, and then in real time, if you are deviating from the schedule, you may be exposed to a penalty depending on if your deviation actually is exacerbating the stress on the grid or not. So they have that to deal with, plus there's uncertainty that comes from any short-term power purchases they have to do. So now, in addition to that, if they have to handle this new regulation, it really gives them the impetus to look for solutions to better manage their supply and demand in real time. And we don't really know for sure, but the expectation is that as we go for more distributed resources connecting to these grids, this situation could become furthermore worse from the perspective of the utility companies.
They'll probably get bankrupt before they solve.
They are dealing with bankruptcy. A lot of them are already dealing with bankruptcy. So the government also has a few other schemes to have a financial turnaround for the distribution companies. Yeah. So the question is, how can SPOReS really help in this? So a few things that are coming out of SPOReS, let me just highlight this. I'm going to talk about this a bit more in detail further down the line, but just to give an idea, a lot of the distribution networks in India are radially connected networks. So that means there's very limited flexibility for any reconfiguration. So if things were to go wrong, if there was any outage on any one of the links, what's going to happen is a lot of loads downstream are going to lose supply. So that would mean that the Delhi government can impose penalties on the distribution company for all the amount of time that it takes to fix that one specific link, right? On the other hand, if you look at any urban distribution networks, many of them are actually meshed in nature. So the mesh essentially provides alternative paths, and you don't have to suffer from an outage for an extended duration of time. Some of them are what they call as weak meshes. So they are not actually a mesh. There are tie lines that you could, which are normally open, and you could just close the tie line to restore supply to parts of the grid. So the question is, we know that having these tie lines could help, but where would be the best bang for the buck in terms of placement of the tie lines? So we want to look at that question, and we want to use some algorithms from graph theory to be able to answer this question. So I'm going to talk about this further down the line, so I'll skip this slide. There's also some focus in India on designing demand response programs now. There's not been a whole lot going on in the demand response area right now, because as we said, we were just focusing more on capacity additions. But now that there's an increasing demand, there are a lot of townships that are coming up. There is a lot of load which is amenable to control. So the question is, can utilities really start engaging consumers in demand response? So if the utility really does want to induce load curtailments via a DR program, there are certain questions we need to know. How many consumers should the utility call? How should the incentives be designed? What would be the information structure that you design for such a program? How much should the utility really indicate to the consumers? So Professor Kulkarni and I have just recently started working on a game theoretic analysis of this entire setup. What would it take to really figure out the incentive structure as well as the number of consumers you should be calling for such a program? So the specific setting we are looking at is you have a voluntary load curtailment program. So the utility just calls on consumers to induce load curtailments, and then it's not a direct load control program, so they are called to reduce curtailments, and depending on whether they participate or not, and what eventually happens in terms of whether there's a supply shortage even after curtailment or not, you could have an incentive structure designed for these consumers on whether they are penalized for non-participation or rewarded for participation. So we have a few preliminary results on how to design incentives for such a setup, but it's still work in progress, so we would be happy to talk about it offline, but there's not much I can present here because it is work in progress. The other thing that's that I had talked about, the brown box could also be a big help in this situation. Instead of doing DR, you could just sort of impose consumption limits on each consumer. Essentially what you could do is the utility has a certain shortfall in consumption, so it could limit consumption at different levels. At feeder level, this is how much you can supply. At the transformer level, this is how much you can supply. And at each consumer level, this is how much they should actually be consuming. So you set consumption limits at each level. That's the utility level problem. So the utility first needs to figure out a fair way of allocating these limits. Whatever is the shortage supply, how do you allocate it at all levels? The second question is, if the consumer now knows this is how much consumption constraint has been placed on him, how does he then do load prioritization? So we have some hardware to be able to do this, and we have algorithms from CS that we are looking at. Professor Kriti Ramamridham's group is actually looking at to be able to do this allocation in a fair and just manner. But as you can see, there are a lot of issues that would come in terms of how do you actually do this fair allocation in a manner that's fair, how much information would the utility really need to be able to do this fair allocation, and so on. So there are a few references here that sort of refer to some of the products that are being developed. we have been looking at smart meter data. Myself and a student, we've been looking at smart meter data to be able to see how much insights can the utility really gain from a smart meter data to be able to set up these consumption limits. Professor Kriti's group, that's right here, has also been looking at response of consumers, how they respond to a curtailment call, and whether that helps them, should you rank them higher, should you rank them lower in terms of calling them again for curtailments, and what should be the incentive structure you design for this. So there's a lot of work already published on this, and again I would be happy to talk about this offline. Any questions as far as this is concerned? Then I'm going to shift gears a bit and then go into the planning and graph theory based approaches to do reliable distribution of power. Okay. So let me just shift gears. So the first problem I had talked about in terms of the Delhi regulation, which was planning reliable distribution networks and placement of new tie lines, that's the part I want to take up now. The motivation for this really comes on the fact that there's a lot of focus now on resilience of power grids. There is, how grids recover from events such as storms, how grids recover from blackouts. There's a lot of focus on how we could build a stronger grid, and what we wanted to do was really look at only the distribution sector. And the reason for that is distribution. If you really look at the electricity sector, distribution is the closest point of connection for any consumer, and many distribution networks typically tend to be radially operated. So any outage on the distribution network has the ability to significantly impact consumers. So we wanted to look at just planning of reliable distribution networks. So just a little bit more on typical distribution networks. These are networks we've taken from the IEEE working group on building new distribution feeders, test systems of new distribution feeders. So this is, I think, a European network, which is typically a low voltage distribution network in Europe typically, which is very radial in nature. This is a more urban network, which is kind of radial as well as meshed. The primary system is radial in nature, and the secondary distribution network is actually meshed. And so the fact that there's a lot of tree-like structure in these distribution networks makes them extremely vulnerable to even single line outages, so to speak. Any single line outage is going to have a significant impact on consumers downstream, and that's going to, so in the context of again the Delhi regulation, that's going to mean a lot of consumers would need to get paid a lot of money by the utility company. So the utility, it's in the best interest of the utility company to really design their network to be more flexible for reconfiguration possibilities. So what we wanted to do was try and augment the existing networks to improve its reliability, and what we want to do is really focus on the connectivity aspects of the network. We want to model reliability as a function of the connectivity, and we ignore things like the network parameters, failure rates, which are typically things that you would see if you were to really look at any reliability from a distribution perspective. We just wanted to suggest new tie lines so that you can have more flexibility in terms of how do you reconfigure the system. So let's take a quick look at an example here. This is the 14 bus system. It's a standard test system. There are already some tie lines present in this system. This 3, the line between buses 3 and 9, 8 and 12, 5 and 14, these are tie lines that are normally kept open, and they would only be switched on in the event of an outage. So for example, if I was to lose the line connecting buses 1 and 2, I could switch on tie line 3 and 9 and restore supply to the loads 2, 4 and 5, which would otherwise not have power because of the outage of link 1 and 2, right? But if you look at this node 10, this node is susceptible to a sustained outage if the line connecting buses 7 and 10 was to go out. There is no possibility for any reconfiguration for this node. That's because there's just no tie line that you could switch this node over to. So as an alternative, if I was to install a new tie line between buses 3 and 10, that could essentially mean that even if the lines between node 7 and 10 was to go down, I could just switch on this link and restore supply to node 10. Now of course, in order to do this, it has to be feasible from an economic perspective, from a physical perspective, and so on and so forth. But that's where the challenge comes. You know, you take some standard sort of graph theory algorithms, you add layers to it and make it amenable to more practical sort of solutions. So I'm going to talk about that now. But any questions on the basic premise? All right. So what we wanted to do, there are other, so just before I go into this, there are other ways that distribution reliability can be improved. You know, people have worked on distribution automation, for example, is a clear sort of solution, right? You, if you are able to locate faults faster, identify the where they are, and do service restoration, that's a very good way to improve distribution reliability. The other things you could do is add a few more protection devices, add new switches that are able to do this automation in a better manner, improve the response times of the crews involved, or of course alter topology by installing new tie lines, which is what we are focusing on. The adding of new tie lines is interesting because it does provide more flexibility for reconfiguration, but the literature that we have seen so far really looks at new tie lines only from the perspective of long-term planning, where they want to look at demand growth and where would new load centers come up and how does the system need to expand to be able to accommodate new loads. So we wanted to do this more from the perspective of just improving the reliability of the system. So we were the motivation came from looking at a problem in communication networks. So what Professor Janusz Belik was talking about today, power networks are not unique. You know, there are a lot of problems in other other equally complex networks, like the communication networks, which we could borrow from. So here we actually borrowed from the design of survivable networks problem, which can come about in the communication systems, and they have edge connectivity augmentation algorithms proposed here to be able to better design communication systems. We wanted to see if this would be applicable to the distribution system problem as well. So what we wanted to do was look at this edge connectivity augmentation and see whether we could use that to identify which tie lines would be important from a reconfiguration perspective. So if you go, going back to the graph I had earlier, if this was my original system and I had two candidates, I could either install a new tie line between buses 2 and 4, or I install it between buses 3 and 5. Which one do I go for? And I can install only one line. Which one would be better? Why? Sorry? I made it easy. So if I was to install a tie line between 2 and 4, what happens is an outage of either link B or D still renders nodes 3 and 5 without a possibility for alternate supply routes. On the other hand, if I was to install this 3 and 5 link, any single line outage, I can easily reconfigure the system to be able to supply all load points then, right? And of course, this could mean that for a transient period of time, I am in an extremely sort of, you know, from a perspective of voltage profiles or losses, this may not be the best way to do it, but at least I would be able to supply the all load points. I may not be optimal, but I may be able to supply all load points. So what is the characteristic difference between this one and this one? In terms of number of edges, they're both the same, but what's different about this versus this is this has the edge connectivity 1, while this has edge connectivity 2. And what is edge connectivity? Edge connectivity essentially is a measure which tells you how many links, what is the minimum number of links I need to remove from a graph to be able to completely partition the graph. And in this case, if I want to partition the graph, I need to remove at least 2 links, whereas in this case, I can remove 1 link and easily partition the graph. So that's essentially what we wanted to look at. We wanted to see if we could come up with edges which improve this particular feature of the distribution system, which essentially then implies that I have more flexibility for reconfiguration. And why is that? That comes from this particular theorem. This is something that's already been established in graph theory. If you had a k-edge connected graph, it means that you have at least k disjoint paths between any pair of vertices. For us, what we are really interested in is whether I have two disjoint paths at least to the source. So if one path was down, I could just resort to another path to get connected back to my substation. So this is the whole premise of the work. Any questions therein? All right. So let's look at the LVNTS network that was developed by, again, the distribution test feeder group. This system is actually radial in nature, so it has edge connectivity 1, because if I lose any one link in this system, I'm essentially going to partition the system into two disjoint subsets. I can improve the edge connectivity if by adding a meshed secondary distribution system. So the network in blue is actually the secondary distribution network, which is meshed in nature, and then the edge connectivity actually improves to 2, and this system is an example of an actual, so let me word this correctly. This was developed by the working group, IEEE PES working group, which is looking at test feeder development, and this is modeled to represent a typical urban distribution network, which tends to be a lot more looped in nature or a lot more meshed in nature. And so the fact of the matter is that when you have a mesh system, you really already have redundancy in terms of number of paths to the source, and single line failures don't really then affect the reliability of the system. So what we wanted to do was distribution networks which are more radial in nature, can we get them to this level of edge connectivity? So just to start off with, you can take the distribution network with all the buses, all the edges in the network, including the existing tie lines and the existing sectionalizers. You take all of that in, model it as a graph, and then we just want to look at, we don't want to look at edge connectivity between any pair of nodes. We are specifically interested in connectivity to the substations, because we want to ensure that there's a path to the source. So we want to make it 2 edge connected so that there are at least 2 disjoint paths to the source. So there are 2 algorithms we looked at. We could either have a unweighted edge connectivity augmentation algorithm, which really just finds the minimum number of edges required to 2 edge connect the graph, or we could look at a weighted edge connectivity augmentation algorithm, which just means that there are more ways I could bring in practical insights into it. So a particular edge might be more impractical and hence costlier, and you could have a higher weight assigned to it, or a particular edge could be really cheap to construct, because it would just mean connecting 2 nodes which are in the same sort of geographical vicinity, and you could assign a lower weight to that. So we have looked at both these algorithms. These are algorithms that already exist in graph theory. We just adapted it for the purpose of our work. Now this is what it would mean if this was the original system I had in I had up there. When I do an unweighted augmentation, what the unweighted augmentation would do is look at all these candidates, all the possible tie line candidates, and really pick the one that gives you the best edge connectivity. But a weighted augmentation, I essentially work with a reduced subset. I may not have all the candidate lines available. I would work with a reduced subset, and then you try to see whether I can do a 2 edge connection by picking up a couple of lines. Now this particular link between 3 and 5, which is the one that's best from a graph perspective to install, may be a very expensive tie line. So you could achieve the same edge connectivity on the other hand by installing a new edge between buses 2 and 5 and buses 3 and 4, which would be perhaps less costly because they are located, co-located, or for whatever reasons this could happen, right? So this is the key difference between the 2 algorithms. So how do I figure out if I'm doing a weighted augmentation, how do I figure out how I'm impacting the overall reliability of the system? So we decided on a few metrics to look at. It's essentially what are the critical lines in the system. So a critical line is the one whose failure would actually disconnect my graph. So in the 14 bus system, if I just go back, I'm sorry to do this, yeah. In this 14 bus system, this 7 to 10, this is a critical line, because if this line was to go down, there's no alternative path available for node 10 to get connected back to the source. And likewise, bus 10 is a critical, it's the affected bus. So which line failure would actually cause which buses would actually get affected by the failure of a specific critical line. So bus 10 is the affected bus which gets no supply if line 7 to 10, the critical line, was outaged. So these were the metrics we looked at. Another metric we looked at also was the number of spanning trees. So it's intuitive to think of in a radial system, we tend to operate the distribution system in like a tree. So if you had more spanning trees in a particular graph, it just implies that you have more flexibilities for reconfiguration. So that was another metric we looked at. And here are a few results. Let me keep a track of time. Okay. So here are a few results. We've looked at some typical distribution systems, the 69 bus system, which is I think the Southern California Edison system, the 84 bus feeder system, and the 136 bus system. These are the number of tie lines you would actually need that actually exist in the system, and these are the critical lines in the system. As a result of, in spite of having tie lines in the system, there are still a few tie lines which are, a few lines which are going to render a few buses incapable of getting connected in the event of certain line outages. So how do you actually go about improving the edge connectivity? If I really wanted to two-edge connect this graph, and I do an unweighted augmentation, it tells me I need 1 extra tie line for the 69 bus system, I need 3 extra tie lines for the 84 bus system, and I need 11 new tie lines for the 136 bus system. So now 11 may be too costly to install. So we also tried to look at how do I, if I was to do weighted augmentation, how would it impact some of the metrics that I just talked about. So there are a few, you can from here, we got a few ideas on what are the kind of tie lines, how do we actually figure out which tie lines really are important from the perspective of this edge connectivity. And you can of course look at these results, but I'm just going to skip one slide ahead. So what I wanted to focus more on now was the fact that, you know, completely two-edge connecting a typical distribution network may be too impractical, it's too costly. So we have to be able to figure out whether we could just do partial augmentation yet have a significant impact on the reliability of the system. And also how do we get in some practical considerations in terms of selecting candidate tie lines. So certain some of these considerations could be things like, okay, what is the economic and physical feasibility of particular tie lines, what are the reliability considerations that go in, what are the regulatory or policy aspects that could impact adding of new tie lines. And what we, the proposed approach we have settled at now is we come up with a subset of edges that at least pass the initial screening in terms of physical feasibility. The economic constraints could come in, economic considerations could come in terms of weights, even the geographical constraints would come in terms of weights, and I'll talk about this just one slide down. And then once you have the right edge weights, you could basically do a weighted augmentation algorithm to improve the edge connectivity. One other thing I wanted to focus on was, while we initially started with looking at edge connectivity, we realized it's actually a very poor metric because it's a very worst case metric. If you look at the graph here and the graph here, they both have edge connectivity 1 because there's this one edge whose removal renders the graph in a partition, right? But you can clearly see that this graph on the left hand side is much better connected as compared to this graph. And if you, instead of looking at edge connectivity, if I look at other metrics like average edge connectivity, it captures the fact that this is a more reliable network as compared to this one. Otherwise, if I just look at edge connectivity, it's going to rank both these graphs exactly the same, which makes no sense. So we now have another metric we are looking at, which is the average edge connectivity. This graph has an average edge connectivity of 3, whereas this graph has an average edge connectivity of 1.67. You can see, so just to see how it would be impactful from an actual test system perspective, we looked at the 33 bus system, which already has a few tie lines in it. Now, if I look at the average edge connectivity of the 33 bus system, it's very close to 2. And the reason it's not completely 2 is because of this particular segment right here. Okay, this is the reason why it's not 2. But if I look at the system without any tie lines in, it of course is completely radial system. It would have edge connectivity 1, average edge connectivity 1, and then as I keep adding one tie line at a time, I can see how it actually impacts the average edge connectivity, and you realize that you get the most bang for the buck if you were to install a tie line between nodes 18 to 33. Now we have played around with a few other distribution networks as well, and what we have typically seen is the larger a cycle you can complete, the better impact you have on the connectivity measures, so to speak. And that's a general lesson to learn. This could also be used to sort of better pick candidate tie lines. Another measure that you could use to rank tie lines by themselves is to really look at what are the average number of paths to source that pass through each edge, and that would tell you essentially how important that edge would be from the perspective of doing any reconfiguration. So how many paths actually pass through it. So you can see that this 18 to 33 tie line, it really is quite important because it's this legend is a bit fuzzy. We tried to do a heat map, but the numbers were very close, so we basically had to do this manually. Yeah, so these are some ways you could basically figure out which candidate lines would actually make more impact on the reconfiguration possibilities. So some other practicalities that you may want to bring in are geographical distances. So we are currently working on looking at algorithms which would allow us to map GIS data into an R2 graph. From the R2 graph we could get Euclidean distances, which we could then use either as weights for the weighted augmentation, or we could use them to model cost as well. We are also looking at a budget constrained augmentation problem. So you have budgets only to allow maybe X number of tie lines to be installed. Which ones, where would you actually locate these tie lines? And a lot of this is already available in a conference publication. We are now also working on a journal publication. Just a few concluding remarks. So we know that there are going to be a lot of interventions required from the planning as well as operational side to make future grids work. The SPOReS team is really trying to develop a whole set of holistic solutions to do planning and operations, guide policy making, guide resource planning, guide resource additions. We are also looking at hardware as well as software solutions to really help manage the supply demand balance in real time. And we would be very happy to engage in any sort of collaboration. Caveat is you have to belong to a few particular set of countries, but we would be very happy to host some of you. So any questions that I would be happy to take at this point.
Questions?
Yes.
So, two questions. So one, so I think the edge connectivity is very nice, like tool. So, but the one confusion I have is this. So once you're adding an edge, so then the power flow will change.
Right.
And then I think the lines they use depending on the power flow. Can we put in those into the algorithm?
So when we add an edge, we are still thinking of it as a normally open switch. So the system is still radial in nature. The edge that we put in is just an extra switch available. So if any other existing a line which was on was to go off, you could use this edge to sort of reconfigure the network. So the system would still be operated in a radial fashion, so it wouldn't alter the flows. But this could perhaps be more relevant if you were looking at this from a transmission perspective, which is already working in a mesh, and we haven't actually looked at many networks that are meshed in nature and how the edge connectivity would alter the flows in a mesh. So we are still looking at edge connectivity in radial networks. We've not looked at edge connectivity in meshed networks. So once we look at that, I would be able to answer that question better. Yeah.
And another one, not very relevant, but when you talk about line failures, I also think about the node failures.
Mm-hmm.
So once they adding more connectivity, it helps with the line failures. I was thinking about another scenario. If I make an error in a node, right, one power plant has some mistake there. If I have less connectivity, that's easy for me to cut. I was thinking about how can I do LND.
Or if there was something wrong with a specific node, you may want to disconnect.
Yeah, once I have more connection in the graph, then it becomes harder to think about how this node failure is going to propagate.
Right. So, but again, the systems that we are looking at here are still radial in nature. So it would essentially, you would need to do the same number of disconnections that you would have to otherwise do to be able to disconnect a particular single node. But there are, I think, metrics that come from a node connectivity perspective. We only looked at edge connectivity, but just like there's an edge connectivity metric, there's also a node connectivity metric that you could look at. And you could even flip the question. Instead of worrying about if a particular node is bad from a system perspective and you may want to disconnect it, you can also think of it from a node connectivity perspective of critical nodes. So there could be certain critical nodes which you want to ensure are better connected than a certain other set of nodes. So priority service, for example, if there was a set of loads that were subscribed to priority service, you may want better node connectivity for them than any other nodes. So you could also, there are other metrics you can look at in graph theory which would give you solutions. We haven't looked at it, but I know they exist out there. Yeah. Yes.
Final question.
So if I understand, you try to improve the reliability of the system by adding some additional links. So did you think of measuring the reliability of the system by something like the expected service interruption costs or something like that that would kind of reflect the economic value if you add an additional link,
right?
But how this impacts?
We have done other work where we have actually looked at the reliability, more standard reliability metrics like SAIFI, SAIDI and so on, which are common in the distribution domain. The main challenge we faced was what would be the failure modeling you do for a new link. That was sort of, we're sort of at this point we're trying to address that specific question. If I was to put existing links which have been in operation for a while, you can sort of do a few statistical sort of modeling to come up with some failure rates for those links. But if I'm putting in a new link, I don't quite know how to, we haven't quite figured out how to model the failure rate of a new link. Once we know that, we already have an algorithm that could help us capture what would be the reliability of this system. So we would then be able to integrate it, but we don't quite know how to model failure rates for a completely new installation. So something that's a new link there, how do you model it? So we don't know the answer to that yet. I don't know if it directly answers your question, but yeah.
Thanks.
All right, thank you.